tweezers and their applications to biological systems. Optoelectronic tweezers is a related technology that uses light-induced bilateral phase force. It allows for the patterned manipulation and high throughput parallel control of microparticles, like this video shows. Optoelectronic tweezers, also known as light-induced DP, utilize a chip with a sandwich structure, a low-power LED light source distribution, generating a dilateral phase phenomenon. This creates a manipulative force on microparticles within the chip, such as cells, microspheres, and nanowires. Technology has a wide range of applications, including the manipulation of microparticles, microassembly, cell patterning, and cell manipulation. While we are seeing a move towards automated manipulation in OET, the throughput capability still leaves room for improvement. Aiming for higher throughput, we are designing chips for large-scale single-cell applications. Naturally, this introduces new challenges for target recognition and navigation. However, we can address this by using deep learning to identify targets and the microenvironment, combined with adaptive light pattern strategies. Here, we use deep learning to precisely identify targets within the field of view. Notice the dashed light patterns. They act as virtual barriers to block the microspheres. However, as you can see, during the movement, the microspheres are squeezed by other light patterns. This causes a loss of control, and eventually the manipulation fails. Through frame-by-frame analysis, we observe that the squeezing effect compresses the available space inside the light stream. Specifically, when the swivel space, denoted as LS, drops below a certain value, the microsphere escapes the trap. Therefore, we introduce a safety distance (DS) into our pace planning algorithm, which is directly determined by that swivel space (LS). When the internal space is too small, the microsphere simply cannot be confined. However, as the swivel space increases, we see a clear improvement. For 10 micro PSBs, we found that a swivel space of 22 microns, reaching a 100% trapping success rate. When microsphere approaches the edge of the pattern, it indicates it is either lagging behind or being squeezed by other patterns. The horizontal force is what allows the bead to keep up with the pattern, and the vertical force, however, is all about stability. If the bead gets pushed upwards, we lose control. By introducing our adaptive light pattern design strategy, we allow the light patterns to merge when they intersect. This significantly expands the swivel space under the same conditions. This means our safety distance (ds) is not determined only by the signals of the light. It makes the pace calculation much lighter and the control much more stable. Furthermore, This strategy handles multi-target encounters, a situation conventionally considered dangerous or unstable. Through the adaptive fusion of light patterns, the system ensures that each bit maintains its required survival space, preventing any loss of control. We can break down these complex interactions into two types: simple one-on-one squeezing and many-on-one squeezing. Our analysis confirms that in both cases, the adaptive strategy allows for a much smaller safety distance. This gives us more flexibility to optimize for computational speed. Simulation results show that in confined species where squeezing is unavoidable, the adaptive strategy is a game changer. It substantially increases the success rate under same conditions. This strategy acts as a fundamental layer for our optical control system, allowing for complex planar movements such as move along the y directions or along the x. And in the right video, we demonstrate the simultaneously automated control or loss of control. In conclusion, within multi-chamber microfluidic chips designed for large-scale single-cell applications, deep learning enables the precise identification of targets and obstacles. By combining this with our adaptive strategy, we achieve automated collision-free navigation within the field of view. Looking ahead, by integrating automated stage scanning, like the XY stage, we aim to scale this up to manipulate over 10,000 targets across the entire chip. That's all. Thank you for your attention.